What's up, guys? Welcome to another video brought to you by The Simple Engineer. Today we are going to be continuing our series for the theory of computation, and what we're going to delve into today is the formal understanding of DFAs, or Deterministic Finite Automatas. One thing that I forgot to mention in the last video that I will be using as a reference guide and some examples that I've taken from is the Sipser book by Michael Sipser. I believe it's edition 2.0 is a good one to use. Any version of the book will clarify any of the ideas that I'm conveying through my videos, but it's pretty much the stereotypical book that you use in this class or this type of coursework in any scenarios. So check that out. You can get it on eBay, Amazon, download it, whatever. So just want to make a mental note. Okay, so back to the idea of DFAs. I really want to talk about the formal definition of a DFA. So we said previously, we talked about in the last video, the DFAs have start states, transitions, final states, things like that. But now we want to say mathematically, when we're writing proofs and we're trying to convey our ideas in a clear and concise way, the mathematical notation that we would be able to talk about this if we were to write it down. So what we say is we say a finite automata, or a DFA, a deterministic finite automata, is represented by a five tuple that contains the following. It contains Q sigma, delta, we have Q naught, and we have F. So what we're going to do is we're going to break this down into the 5 different components clearly so you can understand what each of these mean. So to begin, we have Q, and Q represents in the DFA all of the states, the set of states. Okay, so the set of states, and this is like what I was saying with the nodes. When you have a bunch of nodes, let's say A, B, C. The set of states in this example would be A, comma B, comma C in this set-like notation. So that is Q. Epsilon is the language that is accepted by the DFA, and what we say, it's the finite alphabet. So there's some finite set of information that we can feed into the state. So we have a finite alphabet. Likewise, previously, this is a finite set of states, right? So you can't have infinitely many states in a DFA. There is a finite number that can exist. The third thing is the transition function, or what we say as delta. So this is the transition, and it's represented by the cross product of the set of states with sigma, or the alphabet, which is going to yield some state. So what this is basically saying is, how can I get from one state to the next state based on the input that I feed into it? That's basically what this means formally. So the fourth thing, and we'll look at this, we'll give some examples, so don't worry if this is confusing so far. The fourth thing is the initial state, or the start state. So like what we said in the last video, there's always a DFA with a start state, typically denoted by some arrow. So here the start state would be A. So we have a Q0, which represents the start state. And in this example, the start state would be A. Last but not least, we have the final state, right? And that's what F is. So F is a subset of Q. So it exists in the set of states, but the difference is F is an accept state. So whatever language we feed into the machine, this is where it's going to stop, or this is where it's going to accept. And this is typically denoted, like we said previously, by a double circle. So this is circled twice. So going back through these things, I guess we'll do a breakdown just to illustrate what these mean. So what we said, the states here, we have A, B, C, D. A, B, C, D. These would be the states. The finite alphabet, which we haven't defined yet, but let's say that this is a binary machine, so it accepts different versions of 1 and 0. So if we put in 1, 1, it'll get us to this final state D. If we put in 0, 0, it'll get us to this final state D. Our finite alphabet would be the set 0, 1. These are the two characters that we can feed into the machine for it to be recognized by this machine, right? You can define this however you want. I mean, I could say that the finite alphabet is, Blake, Josh, right? And I could feed in this set, but for every transition, what do I need to say is, okay, I'm going to feed in Blake here. I'm going to feed in Josh here, etc., etc., etc. Okay, so that is what the finite alphabet is. It's either you define it in some examples or they'll define it for you, but this is what the language will be able to recognize. The transition function basically shows movement through the DFA on some input to produce some output, is what this means. So if we're in A and we feed in Blake, we're going to feed in Blake in A, and we're going to get this output at C. So a pretty basic example that you'll see in some mathematical notation is if we're at some node X and we get to some node Y on a 1, we denote this mathematically by the delta transition from X on 1, which is going to equal Y. So this is the state that you're in. So state you're in. This is the input character, and this is the output state that you'll get to on that input. So very trivial idea, but these are things that are necessary to understand DFAs. And when you're proving DFAs or proving that a language is regular, which is something that we'll get into very soon, you're going to have to start with the breakdown of this 5-tuple DFA representation. So what I want to do is actually go through an example that could be, a typical question that you would see or something that you would generate with this idea. So let's just get rid of this. Okay, so the example that I want to give is we're going to build a basic DFA. Okay, so our basic DFA is going to have 3 states. We'll have a state here, and this will be our start state, and we'll denote this by Q1. We'll have an accepting state here. We'll call this Q2, and like I said, the accept states are double circled. And then we'll have another state over here. We'll call it Q3. So Q1 on 0 will loop back to itself. And on a 1, we'll traverse to Q2. Q2 on 1 will stay in itself. And Q2 on 0, go to Q3. And Q3 on 0 or 1 will go to Q2. Okay, so keep in mind, something that you need to understand is that a DFA, any language in Sigma, so any input in Sigma, which in this case is just 0 and 1, this is the alphabet that we define. So for every character in Sigma, you need to have an associated transition for that character out of each node. So if I had 0, 1, 2 in my Sigma alphabet, I would need a transition of 2 coming out of here, going to some node. You can't not have that transition represented. In this case, as you can see here, 0 and 1 are the only 2 characters that exist within my alphabet, and there's a transition out of each node for 0 and 1. So 0 and 1 here for Q1, we have a 1 here and a 0 here for Q2, and we have a 0 and a 1 here for Q3. So we're good. We've satisfied that requirement. So now let's do the DFA breakdown, the 5-tuple. So we say here when we describe this DFA, if we were to describe what it is formally, we would say, okay, we have a DFA M, and you can call it any arbitrary variable you want, but we'll call it M, such that M is recognized by a 5-tuple. And for those of you wondering what a tuple is, it's basically this parenthetical set of data, really. Tuples are used in programming languages, which is like an immutable list. This is basically just a list of data, right? So it's represented by a 5-state tuple M, where M equals Q, sigma, delta, Q0, and F. So we'll say that Q is the set of states, right? So Q equals the set of states, which in this case would be Q1, Q2, and Q3. In addition to that, we have sigma, which is the alphabet that is recognized by M, by this machine. The alphabet recognized by this machine is 0 and 1. Okay, so following the 5-tuple, we have a delta transition function, and delta is represented by all of the transitions that this machine can make. And typically when we generate the delta transition function, we build a table. So a way that we can build a table is we have input 0 and 1, and we have our states Q1, Q2, Q3. And I can just build this grid layout and say, okay, on a Q1, if I put in a 0, what do I get to? I get to Q1. If I'm in Q1 and I put a 1, where do I go? I go to Q2. And then basically you follow this pattern where you just look at the DFA, you see where a transition goes from one state to the next, and you have this grid. And this is what the transition table would look like, and this is how you can describe delta. If you were required to describe it mathematically, you would say, okay, delta, say for Q1 on 0, we would say, okay, delta, if I'm in Q1 and I put in a 0, I'm going to still be in Q1. This is the mathematical representation of that description. The next thing we have is Q0, right? And Q0 is the start state. And as you see here, we have an arrow pointing to Q1. So our Q0 would equal Q1. And the final thing is the set of the final states. And in this case, we just have one final state denoted by this double circle. And this is Q2. So F equals the state Q2. And this is our 5-tuple breakdown. It's very simple. And most of the time, it doesn't really get harder than this. The transition functions can get a little bit crazy. But for basic DFAs, this is the format that you're always going to follow. This is what a DFA is. This is how you represent it mathematically. So with the previous definition, if A is the set of strings accepted by M, we say L of M equals A, or M recognizes A. So here, if we look at this language, right, it can accept, the string 0, 1, 1, right? That's accepted, or it's recognized by the string A. So if we said A equals 0, 1, 1, we could say that L of M equals A, which is the same thing as saying M recognizes A. So I just wanted to make this little side note because it's some typical language that you would see in a textbook or in some examples. So I just want to get this out of the way, that if you do see a language M, a language of a machine equals A, it just means M, the machine M, recognizes the given language. So let's actually use this idea in one last example. just to basically nail it into your brains. And I'm hoping through the rest of these series, this continues to make more sense because I'm going in baby steps to start introducing big topics that are very important for the theory of computation. So going back to that previous idea, we're going to create an example DFA again, a very basic DFA. We're going to have Q1, right? And it's going to be an accept state. And in addition to that, it's also going to be the start state. And on 0, it's going to loop back to itself. And we're going to have Q2. And Q2 on 0 is going to go to Q1. And Q1 on 1 is going to go to Q2. And Q2 on 1 is going to loop back to itself. And we're going to call this machine M3, right? So this DFA right here, very basic, is going to be called M3. So we want to basically create an accepting language for this machine. What does this machine accept? Okay, you see that it takes in some zeros and ones, but what do I do for it to end up at Q1? So we need to practice building up this mindset of understanding, looking at a machine and trying to figure out what can it actually accept if I give it some input. So what I would say is M3 is going to recognize the language where there exists some W such that W is the empty string epsilon, or it ends in a 0. Okay, so let's take a look at this. So we want to say, okay, for me to end up in this final state, for a language to recognize something, it means that at the end of that character input, I'm ended up in a final state, which would be Q1. So here we say, okay, there's this language W, there's a string W, where W is the empty string. So usually in computation, we say epsilon is the empty string, where you literally read in no character, which is understandable here because if we start in Q1 and we haven't even read anything, we're already accepting. So that is a possible combination here. Or, as you can see here, anytime that our string ends in a 0, we're going to end up at this Q1, this accepting state. If I fed in 0, 1, 1, 0, I go 0 here, I go 1 here, and then back to 0, I'm still in this final state. If I put in 0, 1, 1, 1, I never end up. I'm always stuck in Q2 based on this 1. I'll never be in this accepting state. So the language that M3 is going to recognize is anything that feeds in the empty string, which is nothing. I stay in the initial state. Or any string I feed it in is going to end in a 0, like this. So this is basically how you describe the language accepted by the DFA. So that basically concludes this tutorial. I think maybe I'll do one more tutorial kind of delving into some deeper topics for proving deterministic finite automatas, understanding the formality of computation a little bit more, so we can continue through this sequentially to basically better our skills with deterministic finite automata and then other topics involving this idea. So thank you guys for watching. Please stay tuned for the next video.